So we're going to look at GPE and kinetic energy pretty heavily here. Your assessment isn't going to be about this conversion, it's going to be relatively similar. Okay, we're going to be converting some form of potential energy into a form of kinetic energy. So I thought we'd break down really specifically the equation for gravitational potential energy. GPE equals mass times gravity times height. If you haven't got a symbol between, or operation between your symbols, then you know that's multiplication occurring, as we know. It's just a convention of mathematics. Mass is measured in kilograms, gravity is meters per second squared, and we know that on Earth, where most of our problems occur, the gravitational acceleration is 10 meters per second squared, and the height is measured in meters. So I asked us to calculate at the top of Burj Khalifa what our gravitational potential energy. 800 meters is a guesstimate. I'm not exactly sure if it is, but it's about that high. So I would write my working would involve GPE equals mgh. My mass is about 70 kilos. 70 times 10 times 800. Okay, and I would get 5, 6, 2, 3, 4. Something like that, I'm guessing. Is that what we all got about that? In that ballpark, obviously it'll change depending on your mass. Okay. So that was just to get us familiar with what calculating gravitational potential energy is like. And then we moved on to kinetic energy. Now the kinetic energy equation is a little bit more tricky. Only two variables though. So K equals half mv squared. M is mass, V is velocity, kilograms and meters per second. We need it in standard units. If you don't put it in standard units, you're going to get the wrong value. Very important because we're squaring here. And we know that when we're converting between meters per second to kilometers per hour or vice versa, we have a factor of 3.6. So if you're out, you'll be out by a factor of 3.6 squared, which is going to be hard to work with. The only value that is squared is the V. So the M is not squared. A common misconception that students have is that they do this. They square both the M and the V. It is only the V that is squared. So be very, very aware of that. I'm going to ask you to calculate your kinetic energy if you're travelling at 126.5. So whoever is my calculator is going to need to be ready, because I don't know my 126.5 squared off by heart. And what is that? 35 times 1, what's the 126.5 squared? 1,000. 15,000. So, no, that's right. Not bad. Can you times that by 35? 557,000. What's that?
867.
That's okay. I bet that's fine. Now, there's a reason this is out. What do you notice about these two? They're pretty close. Is that the same for yours? Now you've got a different mass, correct? But I'm going to guess you got something pretty similar. Now, one thing you didn't see me doing was I calculated over here using kinematics the final velocity, and I rubbed it out before you could see it, the final velocity that you would be travelling if you jumped off an 800 metre building. And it was 126.49. So what's that tell you? What's happened to my gravitational potential, Alex?
I actually stopped going. Yeah.
What is?
That's like 16,000 and your answer is 560,000.
Okay. 16,000?
Yeah, thereabouts.
And that would be, I'm just going to make it 5,600, so it looks pretty.
It is. It's like a difference of 78.
Yep. Okay. So that's far kinder. So why they're the same? I calculated my velocity if I jumped off an 100 metre building. I shoved that into my kinetic energy equation. I happened to get the same value. Why is that? Why do they equal? Because this is at the top of the building and this is at the bottom of the building.
You're ignoring friction.
I am ignoring friction. That's 100% correct. But where has my gravitational potential energy gone?
You transferred your potential energy into kinetic energy.
So all my energy is being transferred into kinetic energy. So you can use this as a way to find your speed at various points in a fall. Is that far kinder than doing kinematics?
Yeah.
Good. Why didn't I teach you this before I taught you kinematics? Because I'm cruel. I like to see suffering.
You wouldn't get this without kinematics.
What if I wasn't accelerating downwards? What if I was accelerating horizontally in a car? Would that work? So kinematics works for every scenario, whereas this is just good for converting between a falling object. Sweet. Now, interesting that regardless of your mass, I'm going to guess that, we're going to find out in a sec, I'm going to guess that your velocity is going to be the same. So a very common conversion, I'm going to move this over here, a very common conversion that we have to do is to convert kinetic energy to potential energy. Not quite right, but anyway. Sorry, convert gravitational potential energy to kinetic energy. Now, Andrew was right when he raised before that we ignored friction. If we don't ignore friction, these calculations become very, very complicated. Would you expect your kinetic energy to be the same as your gravitational potential with friction? Would you expect it to be higher or lower? Lower. Where's that energy being, it's not lost, where's it being used? Into moving the air particles. So you're giving the air particles kinetic energy. And they're giving you heat. If you jump, who knows what happens when you come back into the atmosphere? What happens to the space shuttle when they come back in? Go on fire, okay? Because it's hitting lots and lots of air particles. If all the GP is converted though, let's assume for calculation's sake that all the gravitational potential is converted into kinetic energy, then we can use that information to calculate our speed at any part of the fall. Now I've put loss there. Why did I put loss there?
Because the gravitational potential energy you have lost is equal to the kinetic energy.
Good. So if I've fallen 1 metre, then I've lost 1 metre worth of gravitational potential energy. Correct?
Yeah.
At the bottom of my fall, I've lost all of it. So if I'm asking you to find the bottom of your fall, then I'm asking you to find all your gravitational potential energy. If I'm asking you, say, a third of the way through, then you're only finding a third of your gravitational potential energy which has been lost. Does that make sense? So we're going to use this information to calculate, and we're going to use the example we had before. But before we do that, I'm going to do a bit of manipulation. Can I manipulate this equation to make it look simpler in any way? What can I do to make this equation look simpler? Is there something on both sides that I could cancel? Mass. So you say if I divide this side by mass and this side by mass, I'll be keeping equivalence. What happens to the m's? So we now know that GH equals half v squared. What I want you to do now is use that information to calculate your speed at the bottom to see if it is 126.5. So using your information, see if you get 126.5.